Hey everyone. So we're doing another example problem, this time with springs. This comes from our back of chapter 9. It's number 28. It reads, a 60 kilogram student is standing atop a spring in an elevator as it accelerates upward at 3 meters per second squared. The spring constant is 2,500 newtons per meter. By how much is the spring compressed? So, just drawing a really quick picture of all this, we have a spring. Let's put a little platform on the spring so our person here can stand comfortably. Boop boop, and they're probably thinking to themselves, why am I doing this? This entire system is moving upwards, and we're accelerating at a rate of 3 meters per second squared. So that's our net acceleration here. If I were to draw a free body diagram, right, I'm going to say I have a couple forces working on it. I have my gravitational force, right, pointing down, mg. And normally we would write a normal force up, but what I think is more descriptive here is that our normal force, our reactionary force to our weight, is actually going to be a spring force. Our spring force, we said, is described by Hooke's law, right? Hooke's law. So if we sum up our forces in the y direction, there we go. I'm going to say that I have my spring force minus my weight. That whole thing needs to be equal to ma net, which a net is this 3 meters per second squared. So if I throw my weight on the other side here, I have my spring force. We'll substitute in just a second for that. Is equal to let's factor out mass, and I have my net acceleration. I'm going to drop saying net. I'm just going to say a plus g. That's that. Now I have numbers for all of these. But I don't want to plug in just yet. I think I want to expand my spring force. And from Hooke's law tells me that I have negative k delta s, or it could be delta y if we want it to here. This is where we're saying that we probably compress downward here from some initial equilibrium position. I'm just going to write delta s is equal to now ma plus g. Throwing k on the other side, delta s is equal to negative ma plus g all over k. If I plug some numbers in, I have 60 kilograms times 3 plus 9.8. That's all in meters per second squared, over 2,500 newtons per meter. I'm going to throw a negative sign there. This negative sign reminder is just telling me how I'm changing the length of this thing, how far either compressed or stretched my spring is. So if I calculate this through, I get delta S equals negative 0.31 meters. That is my compression, and again the negative sign tells me that I've compressed. I haven't stretched. If it was positive, I would have an equilibrium length of my spring here, and I would be stretching it. That would be positive. A negative sign from my equilibrium position, right, my equilibrium length, negative sign means that I'm compressing it. So how much is the spring compressed by? 0.31 meters, because we're just looking for a magnitude here. We know that we are compressing it. So that's this problem. If you have any questions, feel free to email me or swing into an office hour, and happy to talk about it. All right, have a good one.